is Professor D.N. Rao from University of Hyderabad. Professor D. Narayan Rao has been working in the field of lasers and nonlinear optics for the last 3 decades. While doing his PhD from IIT Kanpur in 1979, he worked on multiwatt optical double resonance, crystal growth, fluorescence spectroscopy, and built a CO2 laser for his research work. He was instrumental in the development of the laser lab at Photonics Laboratory, State University of New York at Buffalo, USA. While in USA, he worked on far infrared laser development, transient grating spectroscopy, and spectral diffusion studies in organic solids at low temperature. He was the first person to report the ultrafast response of the polymer systems using a 4-way mixing experiments. He also developed PS and picosecond and femtosecond laser systems. Using them, he worked on many interesting problems in nonlinear optics. He has more than 100 peer-reviewed journal publications and 150 publications in national and international conferences to his credit. He was the convener for the National Laser Symposium held in 1998 and the 8th International Conference on Photonics, Fiber Optics and Optoelectronics 2006. Photonics 2006, organized at University of Hyderabad. After returning to India in 1990, he developed a laser physics and laser quantum electronics teaching lab for the MSc students and an advanced laser research laboratory. His research areas are photonic crystal structures, femtosecond laser direct writing facility, semiconductor quantum dots, supercontinuum generation, and singular optics. Today he will be talking on spectral interferometry, photonic crystals, and nanomaterials for ultrafast switches.
At the outset, I'd like to thank the organizers, and I also thank Prabhu for such a nice introduction. Actually, I wanted to have just 2 from University of Hyderabad, and the organizers took it from our website. Okay, sorry for the long introduction. Actually, I am basically a nonlinear optics person, actually. So when the organizers asked about was back, probably I can give a small presentation. Okay, I thought I just tried to prepare something that is I tried to be as appropriate as possible for the current the theme. So I just brought in the word for the ultrafast switching, where I feel like that's where when somebody talks about the fast computational, probably the switching is something that one should look at. So I will try as far as possible in order to look into these aspects, and I have some 3 or 4. It's maybe sometimes you may find some kind of an incoherence and then hodgepodge. Please pardon me for. I will try to probably integrate them into one talk. See, when Professor Emily Wolf came with spectral shapes, we were just fascinated by that work, and then that is where we first tried to demonstrate the spectral shift in the laboratory using a simple Mach-Zehnder interferometer and using a broadband. That is how we started our work. And probably the interest is still, even today, we still work on the same problem, and now we are working on literally we are working on the spectral switches and how the nanoscale displacements are really they come into the part. When we talk about the spectral, what we talk is not in the space-time domain that we regularly talk about in the regular interferometry. Whereas here we talk about the interference in the spectral domain. So that means spectral domain means automatically we should have a broad spectrum for the source. So we pick up, we make it very, very simple. Though initially we started with a broad light source dye laser, but later on we shifted into the simple white light source, yes, ordinary tungsten lamp or LED, white light LED, and that is what we used it for our study. Now, the moment the path difference is slightly larger than the coherence length of the source, so naturally you will have the spectrum will not show the same kind of a pattern as that of the input spectrum, but it will show some kind of a modifications. How the modifications are going to be exactly, it depicts a picture of the path difference between the two interfering beams. So, larger the interference beams, the closer will be the fringes will become. So, the moment you have infinite very large path difference, so the spectrum automatically you will never have that kind of a resolution, and then it will look again like a patch. So, it will be very, very interesting once you, because white light has a very short coherence length. So, in terms of almost like a micron, so within micron to few hundred, few hundred microns, things become very, very interesting, and we see observation. That is what actually we look at in that region. Of course, there are a lot of advantages, in the white light, with a simple, I mean the interferometry does not cost anything, a few hundred rupees, one can develop the interferometry, and the results, of course, only the costliest one is the detector, because you want, instead of looking at, of course, originally when we started, we did not have even a CCD camera, we just used a simple prism, actually we grating dispersion, and then we tried to see it on a screen and recorded that the spectrum. So, but now we have it's a simple CCD spectrometer would really give a very good path difference. Okay. Actually, I did not put the spectral interferometry here, but in some other, quickly I forgot to put that the one. You can see as the path difference increases, you will see that the spectrum, output spectrum gets modulated quite well. Okay. So, this is here, what we talk, what is the most important here is, the complex degree of spectral coherence. That is what actually right now we are looking at it is, how the output spectrum depends on the degree of spectral coherence. That is what actually we are using both, actually we are using not only with the white light, we are also using with femtosecond generated white light beam to look at the singularities and how the singularities switch and so on. Actually, that is another one which I am not going to touch, but that not only that one with white light, we are also looking at with a femtosecond generated super continuum and then singularities that are come out with us. Actually, the figure I did not show, but that is what it is written over here, that the shift in the peak variance or the sinusoidal modulation within the bandwidth of the whole white light spectrum. Okay. So, you will see a beautiful white light fringes, and of course, this is a simple white crystal, very, very elementary one, the simple the spectrum, output spectrum for the Michelson interferometer, where mu1 2 is our the complex degree of coherence. And what we do is, over the time, we try to see, not only see, because we were using, an ordinary an interferometer, both for Mach-Zehnder as well as Michelson interferometer, we try to develop what is the best suitable geometry to have the least effect on the least effect of the vibrations. So, this is where actually we were trying to see as best as we can see, that we have tried to see the vibrations in the terms of the visibility of the fringes. See, the first one that we are going to talk about is, this the spectral switch in the interferometry. Okay, this is where the geometry of the one that we have used for the looking at the spectral switches. This is simple white light source, it's ordinary any regular lamp. Okay, and then you have the Michelson interferometer, and then look at both in the oscilloscope or the either the photodiode or I mean this is what actually the spectrum I have put, or this is going to be replaced with a your CCD array spectrometer. This is a theoretically generated curve. Okay, as this is when you have path difference between the two beams is 0, then you have the spectral profile is exactly this is what the spectral started spectrum, I mean original spectrum comes out at the output, and when for small path difference of 0.08, 0.3 or 0.8 micrometers, you will see always the red shift in the spectral profile, and for further increase in the path difference, you will see that the spectrum splits into two peaks, and then you will have, this is the position at which where you will have both the peaks will be the same, and so on, then it will get some blue shifted ones, and again it retains back. As you further shift in the increase in the path difference, you get back your original spectrum. Get back in the original spectrum is actually is not exactly the right word, because you will have a small extension in the valence, but which for the first switch one can neglect that one, it almost resembles the same. So, whereas for further distances, yes, you will have multiple frequencies. If I go beyond, let us say 0.1 microns, suppose if I go to 0.3 microns or 0.5 microns, you will see the 3 pulses. Next, you will see further distance, you will see and 4 pulses, 5 pulses, and so on. So now, what actually our interest is, we try to concentrate at this position. So what we have defined this position as the spectral switch position. What becomes important is, what we found out is nothing, I mean, though it was actually this is a Professor Wolf's paper also actually has reported exactly the same one, but what we try to concentrate is on the switch position at which we try to see. So that means if you move slightly even a finite distance on either direction, you come into the either this side or that side. Okay. So what we have defined it as, this is as a spectral switch position. How sensitive it is, that we will see. This is the exactly experimental result. Of course, it exactly comes out as it is recorded as a theoretically generated curve. So it beautifully comes out with the same one. Right. So what we have, this is the spectral modification. This is the, I mean, how the shift is comes. Actually, what I would like to see is this is one. See, if you look at the normalized spectral shift, I mean, with respect to what we define is, like the peak position. So the peak position, what we define is like a red peak or a blue peak, because on one side you have a red peak, on the other side we have a blue peak. If you are sitting on a red peak, we will say that, okay, yes, it is going to be, let us say, on the one side, and when it moves onto I move slightly on the other side, so it goes into the red peak. So I have if I have a 2 detector system where I can detect one onto the blue and one onto the red peak. So I will have an immediate recording of, which signal goes up. So that becomes a very clear indicator, and this sensitivity of this position at which it can change is very, very high. So that means even a few, just we feel that you can, when we try to detect, and we can detect even about a nanometer displacement very accurately through the spectral switch position. So we feel that we can even go up to the pico meter displacements, provided we have such kind of an accurate one. So what actually trying to do is, actually this is what actually we are trying to do. The experiment actually currently one of our student is working on is, we wanted to bring because like getting such a small distances is very, very difficult. So we wanted to create the switch through the nonlinear medium, where just shine a light into the nonlinear medium. We know that, okay, refractive index is going to be for most of the media is n is equal to n0 plus n2i, where n2 is our the nonlinear refractive index, which is very, very small. So even with a small shining of a light, we should see a good change into the refractive index, which is the refractive index again contributes to the path. So that's what we can see, where even to the small distance as much as the few picoseconds. That's what actually we are trying to see, how the output intensity can the change. This is what actually the delay from the this is what actually from the experiments. Okay, and this is what actually we have the spectral shift as a function of delay with the normal dispersive materials. When we do in the when we introduce, see, like we try to do lots of things. What happens if we have a dispersive medium into the one, because the white light is going to have, you know, like an effect. So we have studied how a dispersive medium plays a role, and what kind of I mean the switch effects are going to play a role into the one. This is what one. See, this is more the details into the one. The kind of, you know, like the displacement that we have achieved is with a PZT in one of the arm, and that's what actually we have used for translation. And the white light is a simple 12 watt, you know, 12 volts 55 watt filament lamp. And this is what actually we try to look at, you know, like what happens, you know, like if you do the switch, the recording, you know, like with a simple, you know, give a for a PZT, give a simple signal and see how the switch is going to appear. So that's what actually we try to measure, you know, like how the photodiode is going to see the maximum in the see, like either you put in the blue or put in the red. So where you are going to see either the going up or going down. So this is what actually the reverse, you know, one of the arms, you know, either they put in the red or they put in the blue. So our idea is, you know, like see, because we were working on the switching, most of the time, you know, like the idea is we have been working on materials where we can achieve some kind of a fast switching, or, you know, develop, you know, like use the nonlinear medium to control, you know, the light, how we can do the good, achieve the good switching. So that is when we thought, you know, we decided because, you know, like we have to enhance the, because most of the nonlinear properties are the fast materials have a low value. So in order to enhance, so we thought, okay, we can introduce them into the photonic crystals. That is where actually we try to develop the photonic crystals as a medium for these nonlinear materials. So what we talk about is nonlinear material is say a regular crystal, you know, like when we talk about the regular crystals, you know, when we talk either atoms or a molecule, but when we come into the optical region, since the atoms will not act for diffracting the visible light, so we have to have something which is much more replaces the atom here. So the one has to come into the terms of the micron size particle or submicron size particle from the atom size, that is, which is an angstrom. So the naturally, so the optical analogy becomes, you know, like photonic crystal, which is a periodic arrangement of the macroscopic dielectric media instead of the atoms. So this is where actually we have been working on developing the photonic crystals, which are artificially, which are more like an artificial materials, artificial crystals working in the visible region. Of course, this is a very standard one where the photonic crystals, you know, like one of the in the internet, where, you know, like you have the light, which is light gets really trapped. That's where actually people have been talking about, you know, how the photonic crystals would be really an excellent medium for generating low threshold laser media. We started with first with the one-dimensional photonic crystals. The one-dimensional photonic crystals that we started, actually we started in collaboration with our collaborators in Italy, where we have tried to do the planar waveguides using the sol gel techniques, where we could lay on a glass plate a layers of SiO2 and TiO2, okay, whose refractive indices are different, and we could make multiple layers of almost like 40 to 60 multiple layers, and which would and that is what actually we first studied. Later on, now actually we shifted into the second one, we came to the 3D photonic crystals. Of course, 2D would be a little bit more difficult. Okay. This is what 1D periodic system, which is periodicity is in the one-dimensional direction, and then of course we actually we made our own calculations for calculating the band gap. and this is one dimensional pattern. So our idea is to see that we develop, we are trying, initially we were trying to see, limit our studies into the communication wavelength, which is about 1.5 microns. That's actually one point, sometimes it is easy, and that's where interest was also for the erbium doped systems. So, all our studies were concentrated on erbium doped systems, where we could get a good lasing action, and we could develop also the a good photonic band gap material. Okay. So, this is where actually our idea was to develop a small defect layer, and on the other side, which both, this is a simple your standard diode laser, which is the same thing except that it is in the planar cavity. So, both will act like a Bragg mirror, and then we will have the defect layer in between this one. This is our system is going to be looking like this. Okay, this is our cavity SiO2, where you can have the erbium doped system, and you can also have the other ones are TiO2, SiO2 layers. So, this is what actually the band gap actually is the one, because of the defect you have, because of the defect layer you see that the transmission increases at 1.54. By controlling the proper thickness and proper width, then you can actually move the transmission point over different places, which is actually becomes an advantage of the system. Okay, this is actually the same thing with an erbium doped one. Actually, erbium and ytterbium, actually we have tried to know like how to see there is an enhancement in the lasing action. So, that is what actually we tried to see. Okay, this is another one with a defect layer, getting a different with another one. So, this is actually lot of our work we spent quite a bit of time onto the 1D photonic crystals. Then we tried to move on to the 3D systems. 3D systems, actually our goal is to go into the abnormal structures, which is the ultimate goal is for anybody who is going to be working on the photonic crystals is going to be to come into the abnormal structures. So, the first one we tried was trying to get one of the easy way is because abnormal weight is structures are developed with if you have 3 beams interfering at particular angles which are separated by 120 degrees. Okay. So, you try to you get a good abnormal structures. So, instead of that same thing where we have where we try to achieve instead of the same structures, actually this is what actually I tried in Buffalo by interfering the simple argon ion laser into a simple polymer. So, polymer gets the SU8 material gets polymerized. Wherever the material gets polymerized, and then you dissolve the rest of the material, then you will be left with the abnormal structure. That is what mainly the one. So, the problem and then you will have the band gap supposed to be like you will have a complete band gap with the abnormal structures. Okay. This is sorry, there is one missing, something missing. Yeah, this is the abnormal structures with a one, but the whole problem is the walls are so thin that the system collapses and does not give. It becomes very difficult. So what we have tried to do is we tried to. It's once in success will be one in almost like 20 times or 30 times. Like even few layers, it just simply collapses because the wall thickness is so small. That the conditions are not at all reproducible. So, what we thought the best way is to go for the opal structures. So, where we try to develop a polystyrene beads. So, we developed like a mechanism to make the polystyrene beads of different sizes, particularly in the range of the visible. But the problem is when we wanted to go, we did not have any detector in the range of 1.5 microns because IR detectors are not, we never had the facility for the IR detection. So, and growth of the, we wanted to develop the polystyrene beads into the visible region, which is to come into the visible region. So, the size of the polystyrene beads has to be somewhere around some 2 to 400 nanometers. So, we developed method way to develop like monodisperse the polystyrene beads. Now, we are successful that we can develop get the polystyrene beads anywhere, whatever the region that we want, all the way from almost like 150 to 500 nanometers or even 1000 nanometers we can get. So, that is what actually we tried. Once we the polystyrene beads are obtained, then we can cast them as a like a lift technique, which is where immersion technique, just immerse a glass slide and slowly lift it, so that you will get the photonic crystal forms, which is quite reasonably good. We have been actually we get about some 30-40 layers of the polystyrene beads, okay, which has been reasonably quite good. Some of them right now like some of these are some of the old pictures, but now we have currently 30 to 40 layers of the photonic crystals are good. Now, what actually we are trying to go is an inverse opal structures, where actually we are trying to fill this one with SiO2 and then dissolve this the polystyrene beads, so that we will be left with only the silica inverse opal structures. So, which will be very close to the yablonovite structures. So, that is what actually our goal. We are trying, we are now like partly we have been successful, but the only thing is we have to increase the transmittivity, we have to increase it. So, right now it is only almost like 10 to 15%. So, whereas we have to take it almost like 40 to 50%, which would be quite good. So, if we can reach that 40 to 50% like the inverse opal structures, then it will be good. So, that means this the polystyrene beads now we are trying to dissolve, and we are trying to obtain the inverse opal structures for the photonic crystal studies. Of course, these are the simulated ones like where the programs, and we are also of course making the silicon nanoparticles with mostly for the imaging stuff that we are trying to do. Actually, the another idea that we have been working on is these systems is through the, because we have a femtosecond laser system. So, we have been making use of it for the laser direct writing. So, where we are thinking of creating photonic crystal structures useful for in the 1.5 micron, because going into the about 0.5 microns would be very difficult. So, we decided that okay, we can write the structures and go into the 1.5 micron. So, these are some of the structures that we have been writing. We have been much better successful, like how we have been writing the gratings and different structures, and we are able to create now cavities or change index modifications and so on. So, we are in a position to write subsurface structures, where we think that we can probably get we can go towards the yablonovite kind of structures in future, where we can also introduce into the defects, that if we can create a void, we can try to introduce the defects into the medium and so on. That is what we have been doing. So, actually this is our idea is, of course, this is I have taken it from the literature. Okay, there is like our main idea is not only just write the structures, but also introduce kind of like nonlinear medium, where we can achieve some kind of a bending, and of course, this is the one is like a switching. So, because we are writing now, actually we are working on the two channel, writing the two waveguides, and if we can see that the light can be switched from one channel to the other channel through a nonlinear medium, so that it will be exactly gets coupled. So, we will have a perfect switch. So, this is what actually we are working on currently. And of course, the photonic crystals, like we have already made a first attempt where we have been using this photonic crystal sitting at the right at the band edge, and we are trying to look at the switch. Actually, that is probably the next one. Yeah. Yeah, this is the one actually where we have been looking at the transmittance, actually the one at the right side one, where we have been trying to sit at the edge of the photonic band gap, and by making the a femtosecond laser fall on the medium and see that it is because of the material is most of the materials are nonlinear. So that the band, because naturally at large intensities the refractive index is going to change. So the moment refractive index changes, so the band gap also shifts, so that you will have a completely shift into the the band gap position. Once the band gap position changes, you should have a good switch into the output transmission. So that's what actually we are looking at the transmittance, changing the transmittance with input the light. Actually, this is what actually we have been working now. Because of actually it's mainly as the everybody experiences with the femtosecond laser, it has been down. So we have not able to complete that experiment, but just before coming, this is where the only that is we have tried to see how the shift is comes whenever we look at the intensities. Yeah, this is some of the ones the band gap that we tried to see with the different polystyrene grids, which has been very quite good, actually going almost like 40 to 50% is which is is quite nice. See, the media that we have been working on is developing the switching the systems is which is our for many years we have been working. Actually, I have not put all the results, but the porphyrins and the phthalocyanins. Actually, porphyrins, we did a lot of study with one of my colleague who passed away, Professor Bhaskar Maya. We owe a lot of for our success to him, because he was the one who could supply good materials for us. Most of the porphyrins was synthesized in his lab, and whatever we could request, he could do the modifications, and then accordingly he could give us. So that is what actually we use. Now we are collaborating with another person, probably in Pondicherry, so that we are switching back into the porphyrins. Until the time now we are working on the phthalocyanins, which are given by the IICT, Dr. Giribabu, who is an ex-student of Bhaskar Maya. So this is what actually we are trying to do, how we can achieve the switching with the femtosecond laser. So for this one we have been working on one of the most popular system, which is a Z-scan method, where Z-scan is nothing but simply a system where you focus a laser beam through the sample and look at the transmittance. So once you translate the sample across the beam, so naturally the intensity is going to vary, which is going to be a function of the distance, the position. So that's what we record. So naturally how the medium has the nonlinearity, depending on the medium's nonlinearity. So the transmitted beam shape is going to change. So accordingly you try to find out what how the transmittance, either both you do the nonlinear absorption, also you look at the nonlinear transmittance and try to study the different materials. So most of the time you look at this is one of the material very recently we just looked at it. We found something very interesting result that this is a femtosecond open upper Z-scan data, which is with a concentration of almost like some low concentration. We try to use it so that there is a very small absorption. Okay. With the different intensities, it shows whether it shows a kind of a absorption which is a saturable absorption. Okay, and then the same thing intensity, it becomes saturation absorption remains. At further intensities it reverses, there is a reverse saturable absorption. This is that means because at the focal point, because beam is focused, so at the focal point you have a maximum intensity. Okay. So only when the medium shows a saturation of the absorption, then only you can have the intensity should increase at the center. Whereas a medium which shows more of an absorption at the focal point where the intensity is the highest. So, that means it is exactly a reverse process of the saturation of absorption, what is termed as a reverse saturation of absorption. So, that is what it turns, it switches into from saturation of absorption into the reverse saturation of absorption. Okay. So, at further intensities it still retains that reverse saturation of absorption, which is a very, very good one. So, we found that it is a very strong one, and though with other materials also we had seen, but particularly this material we had seen a very good reasonable intensity. Now, that means we can use if we have looking at the transmitted intensity, if we change the intensity, we should see a change in the intensity going up and down depending on the intensity. We should be working like an optical switch. This is what actually we have been projecting like an optical switch. This is another one with, of course, a slightly a different concentration, and we wanted to show how the concentrations play a role and how switch properties, how much it plays a role. So, we see that a very good the appearance of the switch is like it's quite dramatic and quite good. Okay. This is of course the same thing. The moment actually there are a lot of studies were done. Actually, these are all the, most of the time porphyrins we used to study for optical limiting, which I am not going to touch. All the studies were carried out for the studies in the optical limiting. Where the nanosecond laser is normally used, I mean, so that there is a strong reverse satural absorption is there, so that the intensity transmitted beam can be limited to a particular threshold value, so that it will work like an optical limiter. So, this is what actually we try to use a region in between both. If you see the nanosecond region, and it acts like a like it shows like a particular intensity, it shows like saturable absorption, and then if you see the picosecond, it will have a much smaller, it does not even much longer period. That means there is the way that electronic states behave are responsible is going to make a big difference. So, we have been looking at the excited state dynamics of these molecules, what kind of levels play a major role, what kind of levels do not play, I mean at what time scales do they play the role. So, whether you see like in the earlier in the femtosecond laser, there is a strong 2 photon absorption, which will lead to the saturation, I mean which will lead to the saturation at I mean a 1 photon absorption, which leads to the saturation of the lower excited singlet state, and at higher intensities it starts undergoing a 2 photon absorption, which will go into the higher excited state. So, because the higher excited state has very fast relaxation times, so that actually tries to show that it switches from satural absorption to the reverse satural absorption, while whereas the picosecond time scales are much longer. So, that at longer time scales, you will have like you still have like the state is still it does not undergo the 2 photon absorption. There is more of the saturation of, because relaxation times are very long. I mean it is much faster than the picosecond time scales for the first excited singlet state. So, it keeps showing a saturation behavior for quite some time, and even at very large intensities it does not show the reverse satural absorption. Okay. So, I mean in conclusion, we have been, all our efforts have been like to see that we kind of look at these materials, how they are working for teaching purposes. Okay. And actually I have not included some of the nanomaterial structure, because there are other speakers were presenting quite a bit onto the nonlinear part. So, I just skipped that one. So, whereas we have been working on the same thing, cadmium sulfide, cadmium selenide, and then silver or metal nanoparticles, both core shell structures for the same thing like in the optical limiting or optical switching or bistability in this medium. So that like that work actually we have not presented, but these are all like I mean I have to thank all the first 3 were my earlier students who is there in Venkatraman. Venkatraman is in in Singapore. The other two have been now joined as the faculty members. The Shekhar and Krishna are, and Shadakali are the, Shadakali is working on the photonic crystals, Shekhar and BM Krishna are working on the excited studies, and of course my, the samples we always derive from others, the Giribabu and Gautam Dey in CGCRI, and of course my colleague, with whom I collaborate on the photonic crystals and the inverse opal structures is Maurizio Ferrari. I can now, a couple of my students spend an year there and they come back and do its a collaborative joint program which is sponsored by the DST. And I thank you and the organizers for giving me this an opportunity to present some of the work. I hope I have made it a little bit relevant for the conference, and if not, I apologize. Thank you very much.